Hello and welcome back to Project Guardian. I'm Joe from the Project Guardian team, and today we're going to be talking a little bit about electrolysis, hydrogen gas, and explosions. So in the last video, I talked a little bit about oxy-hydrogen, this magical gas that was going to solve all of our problems. So we're going to talk more about oxy-hydrogen in this video, kind of picking up where we left off in the last video. So first of all, what is oxy-hydrogen? Well, it's basically what it sounds like. It's oxygen and it's hydrogen. I think right about now I'll probably have some sort of something up on the screen, like the chemical formula or maybe like a picture of the molecule, but basically it's O2H2 and it's a gas. It's not hydrogen peroxide. So it's a highly combustible gas, and we're going to try to use this to our advantage in our specific application. Basically, I have a couple nozzles in front of me that we've been testing out, and the basic idea is we're pumping the gas into here, lighting it with a spark plug, and hoping for the best. I mean, I'm being a little under-exaggerating, I guess that's how you would say it. And just because I'm saying that, that doesn't mean that we haven't done a lot of research. We've done a lot of research into this gas, how to produce it, how to make thrust out of it, and how to use this gas safely, because we don't want anyone dying. That would be less than ideal. So the way you get oxy-hydrogen is you basically... Oh, I need my prop. So the way you get oxy-hydrogen is through electrolysis, which is essentially a chemical reaction within an electrolyte where electricity is the catalyst. So basically, the electrolyte we're using is carbonic acid, which is H2CO3, and that's basically you just mix baking soda and water together and it forms carbonic acid. So you put this through essentially a reactor, which has a cathode and an anode, and electricity gets passed through, which basically is the catalyst for the chemical reaction, which separates the oxygen and the hydrogen in the water into O2 and H2. And actually, I think it's 2H2 and then O2, because it takes two H2O molecules and turns it into two H2 molecules and one O2 molecule. And so our reactor right here, it's basically just a PVC tube with a cap on one side and a screw cap on the other. And this is the port input for electrolyte. So basically there's a reservoir of electrolyte of the carbonic acid. It gets pumped through and floods the reactor. And then at the top we have a little push to connect valve here that for electrolyte out, as well as the oxy-hydrogen out. And so if we unscrew the top here, and you kind of labeled it on the top positive, just because this one's easier to clean and the positive one will corrode a little easier and have sediments deposited on it and whatnot. But essentially what our reactor is it's a bolt with some washers. And all of the washers are sanded down so that they have the maximum surface area, because essentially this chemical reaction is a product of the surface area that you have and the amount of electricity you pass through and whatever electrolyte you use. Basically, you want to have the kind of the sweet spot where you have as much surface area as you can and then the right amount of electricity to produce the most gas as possible. For us, we actually had to choose these bolts and washers because we couldn't find economically feasible stainless steel supply. Went with the bolts because they were a lot cheaper and a lot easier to find. Also, this thing on the side is just a shunt resistor so that we can measure the amperage and voltage going through the reactor, so we can do some calculations that we came up with. So from the reactor, it then goes to a charge tank, and this charge tank basically is flooded with the electrolyte, in addition to the actual reservoir of electrolyte. And I don't have the tank with me because it's like that big. It's not very heavy, but I think there's still water in it, and I didn't really want to take it in here and get everything all wet and then have to clean up, so sorry about that. So the gas gets pumped into the top of the tank, which then displaces some of the electrolyte, and then there's a purge valve at the bottom which goes back to the reservoir of electrolyte, so that when the air goes in, it displaces the electrolyte, pushing it out so that it makes room for the air. Basically, this ensures that there's only going to be the oxy-hydrogen in the tank, so that there's no other air like nitrogen, carbon dioxide from the just surrounding air, because we want that perfect stoichiometric ratio between the oxygen and hydrogen. We don't want any other gases mixed in there. So then from the tank, there's a solenoid valve on the top, and I actually do have this assembly here. Alright, so this is the assembly on the top of the tank. That's where it connects to the tank. There's another purge valve on the top here, so I can easily flood the tank with the electrolyte instead of having to keep the solenoids open and get this pressure regulator all wet inside, which usually is not advisable. You want this to only be air, so that's why we have this valve over here so we can do maintenance work. But under normal operation, this would be closed. So let me do that. So the gas would go up here and wait at the solenoid valve. Once the solenoid valve is open, it would go to the pressure regulator. And this pressure regulator does exactly what it sounds like. It regulates the pressure. Basically, how it works is there's kind of a valve in here. And then there's just this pressure gauge that tells you how much pressure is behind it. And then to this other solenoid, basically I did these two solenoids just so that I can check the pressure in the tank without actually pushing all of the gas out through everything. It's kind of redundant, but that's alright. So from this, it would then go to the flashback arrestor, and I will note that we will be making a change to this because the gas is not getting enough, it's not getting pressurized enough inside of the charge tank, so we're actually going to have to add an air compressor and then another pressurized tank or pressure tank for the gas to actually go in. So that will go in between where this solenoid is. Just for kind of my future reference as well as yours. After that, it's basically going to go into the flashback arrestor, and we have one here. Just slapped myself in the face with a wire, or tube, or whatever it's called. So this would be the long line that goes into the nozzle over here. But basically, this is what you call a bubbler. And what it does is exactly what it sounds, it bubbles. There's water in here up to about right here, and what that does is the gas will go in through this tube from the pressure tank through the pressure regulator. So it'll come in through here, and then it'll go into the water, and then it will bubble up through the water and then go out here. This little assembly is a pressure purge backflash pressure purge valve, which basically when a backflash happens, this little valve will open a little bit and let the pressure go out, so that it doesn't compress this and explode the flashback arrestor. And so basically this just prevents, if there is a backfire of the nozzle, it prevents it from going all the way back to the pressure tank or the charge tank and exploding the tank, which is, generally good. We don't want to explode things in that manner. We want to explode them in a controlled way that we can, control. That's the purpose of this guy. Then this would go to the nozzle, which I also have the most recent nozzle with me right here. And there'll be a link in the description to the actual design drawings for it. I think it'll be in the description, or in the iCards or something like that. Are they called iCards or are they just called cards? I don't know. So this is the most recent iteration of nozzle design we have. Previous ones had bigger area ratios and smaller throats, and they didn't have a fuel manifold. They just had fuel injectors in the side. You probably can't see this. They're all 3D printed out of PLA, which is very meltable with the high temperature that this gas burns at. So these are just for testing. They're not for the final product. So this then goes to, from the spark plug, it goes to a coil, and then that coil basically ups it from 12 volts to 24 volts, and then there's a MOSFET on that coil that will turn the DC 12 volts into 24 volts AC for the spark plug. And I think we're running that at, we've done a couple tests at a bunch of different frequencies. I think in the description and the iCards right about now, there'll be a little compilation of all the failed tests we've done, which is kind of amusing. So you have that to look forward to, and I have that to look forward to edit. I am actually filming this video on the day it's supposed to release. I've kind of been procrastinating a little bit on this video, so if it doesn't come out on the 21st of June, then I don't know. Blame my procrastination. So that's basically our system here for the oxy-hydrogen to produce thrust from it, that is. Um, so we're still working on the nozzle design and the system. We're tweaking it, trying to get it just right so that we can produce the maximum amount of thrust possible. I only recently was able to get this nozzle not to backfire, and so we're getting there. But it's a lot of research, a lot of learning, and it's just a process. It's the engineering design process, and it just takes a while. These things take time, so just bear with us, and we are doing things. Kind of the next parts of this phase of the project, for those of you who don't know, we are in phase 1 of our project, which is the research phase. We're basically getting all of this research together, figuring out the technology, getting it down to a... So then we can actually know what we're doing when we go to make the final prototype. So that's where we're at. Kind of the next steps that we have are we need to finish the nozzle design and testing. We need to add that air compressor, and then I have it here that a video will be out in 1 to 2 weeks with a breakdown of the whole system, how we built it, designs, etc. I kind of did that here, so I might rethink that. But I know there will be a video out in 1 to 2 weeks. It'll be part 1 of a 2-part kind of video essay, I guess. And it's going to be about testing the nozzles and kind of our system in general. So I guess that is accurate. But the first part's going to be about our system, seeing it run, and kind of some in-depth stuff there. And then the second part will be the nozzles, testing it, seeing how much thrust we get out of it. So you can expect the second part to be out maybe in 4 weeks, maybe 5, depending on how productive we are and how much work we get done. So yeah, just bear with us. I think that's about it for the video. If you could like the video, subscribe is always a good thing, and it's free. So yeah. And if you have any comments, questions, concerns, any feedback, any like, I don't know, if you have any experience in producing thrust from oxy-hydrogen, I'd be more than willing to chat with you. But yeah, if you have any feedback, any comments, you know where to leave them. So I think that's it for me. Signing off.